Hello everybody. Today we are going to see examples of Fourier series with period 2L. Expansion with period 2L. So let us see first example. Find Fourier series expansion of the function f of x, which is given by f of x equals to pi x for 0 less than or equal to x less than 1, and it is pi into 2 minus x for 1 less than or equal to x less than or equal to 2. So as all of we know, the Fourier series expansion of any function f of x is given by f of x equals to a0 by 2 plus summation an cos n pi x upon L plus summation bn sin n pi x upon L. And since here in this case the L, the half period is 1, because the period is 0 to 2, that is 2. So L is 1. So we can write this Fourier series in this case equals f of x equals to a0 by 2 plus summation n varies from 1 to infinity an cos of n pi x upon L, L means 1 here, plus summation bn sin n pi x upon 1, n varies from 1 to infinity, where this a0 now we will calculate. It is 1 upon L means 1 upon 1, that is 1, integral 0 to 2 f of x dx. Now this function f of x is defined in two subintervals 0 to 1 and 1 to 2. So we split this integral according to 0 to 1 it is pi x plus 1 to 2 it is pi into 2 minus x. So integrating this and simplify, pi integral of x is x square by 2 within the limit 0 to 1 plus pi integral of 2 minus x is 2x minus x square by 2 within the limit 1 to 2. Put the limits and simplify. So when you put upper limit 1 by 2 minus lower limit is 0, so pi into 1 by 2 plus for this second term upper limit when you put 2 x equals to 2, this is 4 minus 2, that is 2, and when you put lower limit 2 minus 1 by 2, that is minus 3 by 2. So simplifying this, you will find it is pi into half plus half, that is pi. So a0 equals to pi is our first value. Now we will calculate an. An again it is 1 upon L means 1 integral 0 to 2 f of x cos of n pi x upon L. L is 1 again, so it is cos n pi x dx, f of x cos n pi x dx. So this integral can be split in these two intervals, sum of these two intervals 0 to 1 f of x is pi x into cos n pi x dx plus summation 1 to 2 f of x is pi into 2 minus x into cos n pi x into dx. Now we will evaluate these integrals and we will find the value of a. So, okay, I will erase this. A0 we have already obtained, it is pi. Is it okay? Okay. Now we are calculating an. So here continuing the calculations, an equals to this first integral pi you can take outside, integral of x cos n by x. First function, integral of cos n by x is sin n by x upon n pi minus derivative of this x into integral of sin n by x is minus of cos n by x upon, here it will be n square upon pi square within the limit 0 to 1 plus the next term pi you can take outside. First function 2 minus x, integral of cos n pi x is sin of n pi x by n pi minus derivative of this is minus 1, integral of sin n pi x upon n pi is minus of cos n pi x upon n square pi square. This is within the limit 1 to 2. Substituting the limits and simplifying. When you put upper limit here, sin of n pi is 0, minus minus plus, cos of n pi is minus 1 raised to n upon n square pi square. So when you put lower limit, 0 into anything is 0, minus minus plus, and again it is minus, so cos of 0 is 1 upon n square pi square plus pi into. Here when you put upper limit 2 minus 2 is 0, minus 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 of cos n 2n pi is 1. Again when you put lower limit, sin n pi is 0, so this term becomes 0, minus minus minus, again minus is plus, cos of n pi is minus 1 raised to n upon n square pi square. Simplifying this, pi upon n square pi square, from every term we can take common out. So here remains minus 1 raised to n minus 1 plus this is minus 1 plus minus 1 raised to n. That is nothing but this is 2 times pi n square in bracket minus 1 raised to n minus 1. So this is an. This implies an equals to 2 times minus 1 raised to n minus 1 upon pi n square. Now we will calculate Bn. Bn equals to, again 1 upon n is 1, integral 0 to 2 f of x sin of n pi x upon 1 into dx. Again we have to split this integral into sum of these two integrals, 0 to 1. F of x is what it is defined, pi x sin n pi x dx plus integral 1 to 2. F of x is pi into 2 minus x into sin of n pi x into dx. So evaluating these integrals and simplifying. So this equals to pi into x sin n pi x, integral of this first function x, integral of sin n pi x is minus cos of n pi x upon n pi minus derivative of x is 1, and integral of minus cos n pi x is minus of sin n pi x upon n pi, that is n square into pi square. So here completes this first integral, limits are 0 to 1 plus pi, again you can take here common. First function 2 minus x, integral of sin pi and sin n pi x is minus of cos n pi x upon n pi minus derivative of this is minus 1 into integral of minus cos n pi x is minus of sin n pi x upon n pi, that is n pi n square pi square within the limit 1 to 2. Substituting limit and finding the value of this bn. So I will erase this. Okay. The value of an that we get, I will write here. An equals to 2 into minus 1 raised to n minus 1 upon pi n square. Now continuing finding this value of bn. So if you simplify this is pi. When you put upper limit 1 cos of n pi, 1 is minus 1 raised to n, minus of minus 1 raised to n upon n pi. When you put x equals to 1, sin n pi becomes 0. So that all limit becomes 0. When you put x equals to 0, this becomes 0, sin of 0 is 0, the lower limit is 0. Here this is plus pi. When you put upper limit x equals to 2, this term vanishes. When you put x equals to 2 here, cos n 2n pi is 0. 2n pi is 0. So upper limit is 0. When you put lower limit, minus 2 minus 1 is 1. Minus of cos n pi is minus 1 raised to n upon this n pi is there. And when you put x equals to here, sin n pi becomes 0. Simplifying all these things. So I can take common out here. So what remains in the bracket is minus of minus 1 raised to n upon n pi, and here minus plus. So that gives us 0. So bn equals to 0. Now put these values of a0, an and bn in this expansion. F of x equals to a0 by 2, that is pi by 2, plus summation n values from 1 to infinity. An is 2 times minus 1 raised to n minus 1 upon pi n square into cos of n pi x upon n. L is 1 here. Plus next term will vanish as bn is 0 for all n. Now simplifying this, what you will find, pi by 2 plus here 2 by pi I can take outside the summation, 2 upon pi. Inside summation I will put the values of n. N equals to 1 when I put minus 1 raised to 1 is minus 1, minus 1, minus 2, minus 2 upon pi 1 square, that is pi. I can write 1 square, okay, into cos of pi x n equals to 1. When I put n equals to 2, minus 1 raised to 2 is 1, 1 minus 1 is 0, so second term vanishes. Then when I put n equals to 3, minus 1 raised to 3 is minus 1, minus 1, minus 1, minus 2 upon here pi into 3 square cos of 3 pi x. So putting on these values, when you put n equals to 4, it vanishes, n equals to 5, it gives minus 2 upon pi into 5 cube cos of 5 pi x and plus and so on. So from each and every term you can take minus 2 common now. So pi by 2 minus 2, when you take outside, this become minus 4 upon pi. Inside the bracket we will have cos pi. Oh sorry, already we have taken this pi outside, so we need not to write this pi here. So only 1 square, 3 square, pi square like that. Okay. So cos pi x upon 1 square plus cos of 3 pi x upon 3 square plus cos of 5 x upon 5 square. This is 5 square plus and so on, like this. That also we can write in the form of summation as pi by 2 minus 4 upon pi. If I write this as a summation n varies from 1 to infinity, I can write this as cos of 2n minus 1 pi x upon 2n minus 1 square. So which is the required Fourier series expansion of the given function f of x.